Hi, my name is Bram, and I'd like to tell you something about my PhD project on multi-material additive manufacturing using the discrete element method. The goal is to create a simulation from actual printer inputs. So you want to use the G code, which describes the print path, the printer settings, and material parameters. And with this, we'd like to simulate, which is often hard due to the large variety in scales. Think of length, time, and temperature. And we would like to generate output to look at the temperature and stresses at every time step during the printing process. To achieve this, we need to include the following in our discrete element model. We need thermomechanical coupling. We need to describe all the forces in there. We need conduction and a heat source. And we need to make a clear distinction between powder and solid interaction. And finally, we need to correctly describe the boundaries and material deposition. To achieve all this, we can do the following with our simulation. We can simulate heat conduction over time. We can see that the discrete element method correctly follows the finite element converged simulation, both for a solid and for a powder. We can also simulate solid material properties, so we can perform a compression test, deduce the forces and the strains, plot the stress-strain curve, and then deduce the Poisson's ratio and the Young's modulus. We can see that we can actually capture a solid material, and we can run a small additive manufacturing print, an H shape in this case. We can look at the temperature and stresses at each time step during the print, and we see that the print warps during the process. And that, in a nutshell, is my PhD project.